This is chapter 6 on alternating current. So from our lecture, we have learned that alternating current means that the current magnitude and direction is changing periodically. That's why changing periodically in our syllabus will be sinusoidally changing. In this case, we have our equation for current to be I equals to I naught sine omega t. Okay, this is our formula. So from the formula, we draw this graph, this sine graph here. Okay, based on our formula, based on our syllabus, it's I equals to I naught sine omega t, but it can be cos, it can be sine omega t plus phi. The current is sinusoidally varying, but you can have different phase shift that happens to the current. But for our syllabus, we restrict it to I equals to I naught sine omega t. So you need to know that I stands for the current at a specific time, or we call it instantaneous current, okay, at a specific moment. Whereas this I naught here represents the peak current, which is the maximum possible current, maximum possible instantaneous current achieved by the circuit. Okay, sine omega t, the omega here is similar to your chapter 9 from simple harmonic motion last semester. So that will be on angular frequency. Of course, t will be the time, which is the time t that we mentioned over here. Angular frequency can be related to period, can be related to frequency. So this is similar to what you have learned in chapter 9 simple harmonic motion last semester. So the three formulas as shown here, omega equals to 2 pi over big T, omega equals to 2 pi f, and t is the inverse of frequency. Okay, so we learned about peak current. There's also another value, another representation that we need to know, which is the root mean square. Okay, so besides having the peak current, we also have root mean square current. Root mean square current here, root mean square is being created because it represents the value of the sinusoidally varying current better. What I mean is, if you just represent this whole sine curve here with I naught, then it is not representative enough of the whole sinusoidally varying curve. IRMS will be a better representation of the current in this AC circuit, because if you take VRMS times IRMS, you can derive a better representation for the power of the AC circuit. But for this one, we'll discuss it at the end of this chapter 6 here. But IRMS and VRMS will be a better representation because it can help us to determine the average power better. Okay, so that's a general thing you need to learn about alternating current. So let's try and apply what we have learned in a few questions. Question 9. The graph shows the variation of a sinusoidal AC with time t. Okay, so we are asked to find the peak current. So if you are asked to find the peak current, I believe the question should be easy enough for you. You just look at the graph, see where's the maximum possible value for current. So that's 5. So from here, we can determine that our peak current, which we call it as I naught, is equals to 5 ampere. Okay. Second question, what's the RMS value of the current? RMS value will be somewhere around here. Okay, so this will be our IRMS, but it's not something that you can determine from a graph straight away. In order to determine the RMS value, what you need to do is you need to relate it to the formula that we learned in the previous slide. This formula here relates between I naught and IRMS. Okay, so what should we do? We should write down the formula first. IRMS is equals to I naught divided by square root over 2. So from there we know I naught is 5 ampere. Therefore IRMS will be equals to 3.5 ampere. Okay, so that's our RMS value for our current. Let's move on to C. C asks for the frequency of the current. In order to obtain the frequency, we have to know that frequency you can obtain using various ways. For this case, it's just current only. There's no relation to voltage. So if it's just current and it's just a graph, we have to deduce it based on the three relation that we mentioned just now. omega, period, and frequency, they are related to each other. From the graph, you are able to obtain the period. And what they're asking for the frequency. So to express the relationship between these two things, you have the equation T equals to 1 over F. Okay, or F is equals to 1 over period. So from this relationship over here, what can we do is F is equals to 1 over T. Then we need to determine the period, and the period is just a time taken for the current to go through one single wave cycle. So that will be 40 milliseconds. So be careful, 40 milliseconds is 40 times 10 to the power of -3. Okay, so from there, we are able to determine the frequency to be 25. But for the unit of frequency, you have to be very, very careful. It's hertz. Okay, hertz also has another meaning, which is per second. So it means by when I say 25 hertz, it means this current here will go through 25 complete wave cycle. So you go through 25 times this kind of wave cycle within 1 second. That's the meaning of 25 hertz. Okay, so last one, the change in phase in a time of 15 milliseconds. So I didn't really explain very explicitly what is change in phase, but for our situation just now, let's say I is equals to I naught sine omega t. Whatever that is inside our trigonometric bracket, this is our trigonometry, the sine, whatever inside our trigo bracket, that will be called the phase. Okay, so if today you happen to have another equation, let's say your I is not represented by this equation, your current is represented, let's say, by cos, then you have omega t minus phi, let's say. Then again, your phase will just be everything within the trigo bracket, everything within the sine bracket. That's why your omega t minus phi will be your phase. Okay, in this case, you can see that it's a clear sine curve. It's just a I equals to I naught sine omega t curve. Okay, so our phase will be equals to omega t. So we need to find the change in phase. Okay, change in phase. I still don't really prefer to write the phi because phi is usually used to represent phase angle. But in this case, they're asking for change in phase. Let's just write change in phase. Then that will be equals to the phase final minus the phase initial. Okay, the phase final will be omega t final. The phase initial will be omega t initial. So we know that the omega doesn't change, our angular frequency never change, so we can bring out the omega, then you are left with t final minus t initial. And that is just the duration that is being given in your question. This is just the time duration. Okay, so from here, what are you able to do is, you can just relate it back to omega, then the time duration. And from here, you can do a substitution. Omega is just 2 pi f, then time duration, 2 pi. Our frequency is 25 hertz. Our duration is 50 milliseconds. So if you calculate everything, you should be able to get the answer of 3 over 4 pi, which is also equivalent to 2.36 radian. So this is how much phase has changed throughout this duration of 15 milliseconds. Okay, so you can think of it as the current probably starts here, then after 15 milliseconds, then you end up here. Okay, and how much phase has changed? If you look over here, it's 3 over 4 of a pi. A pi will be having a distance from here to here, right? Because that's half of 2 pi. Half of 2 pi means like half of the wave cycle. So this one will be pi. So 3 over 4 will be about here, then here should be 3 over 4 pi, and if you see it, that's equivalent to 15 milliseconds. Okay, so 15 milliseconds is equivalent to 3 over 4 pi of this wave cycle of the current. Okay, so that's it for this question.